Picture this, an echelon form with two free variables, and you're grinding through back substitution. Plugging values up row by row, simplifying, collecting terms, half a page of algebra. Now look at the same system in reduced row echelon form. The RREF is obtained from U by dividing row 2 by 2, then subtracting 2 times row 2 from row 1. The result is the matrix with rows 1, 2, 0, negative 2, then 0, 0, 1, 2, then 0, 0, 0, 0. The pivot columns are columns 1 and 3. The free columns are columns 2 and 4. Circle them. Now here's the magic. Just negate the entries in those free columns, and both special solutions appear immediately. For the first special solution, set x2 equal to 1 and x4 equal to 0. Reading off the negated free column, 2 gives x1 equals negative 2, and x3 equals 0. That's the vector negative 2, 1, 0, 0. For the second special solution, set x2 equal to 0 and x4 equal to 1. Reading off the negated free column, 4 gives x1 equals 2, and x3 equals negative 2. That's the vector 2, 0, negative 2, 1. Every special solution was already sitting inside the matrix waiting for you to read it. That's the power of RREF. Let's build this form. We start with echelon form U from the previous lesson. Row 1 is 1, 2, 2, 2. Row 2 is 0, 0, 2, 4. Row 3 is all zeros. Now the pivots sit at column 1, row 1, and column 3, row 2. Standard elimination zeros are entries below the pivots. Reduced row echelon form goes further. We eliminate upward and scale every pivot to 1. Here's the definition. A matrix is in RREF when 3 properties hold. First, every pivot equals 1. Second, all entries above and below each pivot are 0. Third, 0 rows sit at the bottom. Let's get there in 2 operations. First, we zero out the entry above the column 3 pivot. That's the 2 sitting in row 1, column 3. Replace row 1 with row 1 minus row 2, entry by entry. 1 minus 0 gives 1, 2 minus 0 gives 2, 2 minus 2 gives 0. The target entry is gone. 2 minus 4 gives negative 2. The matrix is now 1, 2, 0, negative 2 in row 1. Row 2 stays 0, 0, 2, 4. Row 3 stays all zeros. Right? Second, we scale the row 2 pivot to 1. Divide row 2 by 2. Row 2 becomes 0, 0, 1, 2. Here is R, the reduced row echelon form. Row 1 is 1, 2, 0, negative 2. Row 2 is 0, 0, 1, 2. Row 3 is 0, 0, 0, 0. Let's check. Pivots are 1. Zeros above and below each pivot. 0 row at the bottom. All 3 RREF properties hold. Now let's look at R and find its hidden structure. Start by highlighting the pivot columns. Columns 1 and 3. Column 1 reads 1, 0, 0. Column 3 reads 0, 1, 0. If we extract just the pivot rows from these 2 columns, we get the entries 1, 0 in the first row, and the 0, 1 in the second row. Together they form the 2 by 2 identity matrix, I sub 2, sitting inside R. Now highlight the free columns, columns 2 and 4. Looking at the pivot row entries, column 2 gives us 2, 0, and column 4 gives us negative 2, 2. These entries form a 2 by 2 matrix F. Row 1 of F is 2, negative 2, and the row 2 of F is 0, 2. So R contains 2 blocks woven together, the identity I in the pivot columns and the matrix F in the free columns, with a row of zeros at the bottom. If we mentally rearrange the columns to put the pivot columns first and the free columns second, R would look like a block matrix, I and the F on top, and zeros on the bottom. A block matrix means a matrix partitioned into smaller submatrices. This block view is the key to everything that follows. Write the system Rx equals 0 in block form, split X into pivot variables and free variables, and the equation becomes the block matrix with I and F on top, zeros on the bottom, multiplied by X pivot stacked over X free equals the 0 vector. From the top block row, we get I times x pivot plus f times x free equals 0. Since I is the identity, we can solve directly. X pivot equals negative f times x free. Now here is the key trick. To find every special solution at once, set x free equal to the identity matrix. Each free variable takes the value 1 in turn, while the others are 0. Then x pivot simply equals negative f. Stack the results together. The null space matrix N equals negative f on top and I on the bottom. The columns of N are exactly the special solutions to Rx equals 0. We've got the structure. Now watch how fast these solutions appear. From R, the matrix F sits in the free columns at the pivot rows. F equals the matrix with entries 2, negative 2 in row 1, 0, 2 in row 2. Negated, negative f is negative 2, 2 in row 1, 0, negative 2 in row 2. Now we build the null space matrix N column by column, reordering the rows to match the natural variable order x1, x2, x3, x4. For the first special solution, we take the first column of negative f, which gives the pivot variable entries. x1 gets negative 2 and x3 gets 0. The first column of the identity gives the free variable entries. x2 gets 1 and x4 gets 0. Assemble the vector negative 2, 1, 0, 0. For the second special solution, the second column of negative f gives x1 equals 2, x3 equals negative 2. The second column of the identity gives x2 equals 0, x4 equals 1. Assemble 2, 0, negative 2, 1. The final null space matrix N is the 4x2 matrix with columns negative 2, 1, 0, 0, and 2, 0, negative 2, 1. These match the back substitution results from the previous lesson. Same answers, no algebra. Here is the most common stumbling point. In the formula, N equals negative f on top, I on the bottom. That looks like neat, separated blocks, pivot rows stacked together, then free rows stacked together. But in the actual vector, the rows interleave. Pivot variables get their entries from negative f, and the free variables get their entries from the identity, but they alternate according to the original variable ordering. In our example, the pivot variables are x1 and x3, so rows 1 and 3 of each special solution come from negative f. The free variables are x2 and x4, so rows 2 and 4 come from the identity. Let's trace this carefully. x1 is a pivot variable, so its row comes from row 1 of negative f, giving us negative 2 and 2. x2 is a free variable, so its row comes from row 1 of I, giving us 1 and 0. x3 is a pivot variable, so its row comes from row 2 of negative f, giving us 0 and negative 2. x4 is a free variable, so its row comes from row 2 of I, giving us 0 and 1. That is how we get N equals the matrix with rows negative 2, 2, then 1, 0, then 0. Negative 2, then 0, 1. Always track which variables are pivot and which are free. The formula only works when you slot entries into the correct positions. Let's reinforce the recipe with a different shaped matrix. Take a transpose, a 4x3 matrix with rows 1, 2, 3, then 2, 4, 6, then 2, 6, 8, then 2, 8, 10. We reduce this to reduced row echelon form. I'll spare the row operations and jump straight to the result. R equals, row 1 is 1, 0, 1, row 2 is 0, 1, 1, and rows 3 and 4 are all zeros. The pivot columns are columns 1 and 2, which form a 2x2 identity block. The single free column is column 3, giving f equals the column vector 1, 1. So negative f is negative 1, negative 1. Now we build the null space matrix N. Since the pivot columns are already columns 1 and 2, and the free column is column 3, the structure is straightforward. N has 3 entries. Rows 1 and 2 come from negative f, giving negative 1, negative 1. Row 3 comes from the identity for the free variable giving 1, right? So n equals the vector -1, -1, 1. Let's do a quick check. A transpose times this vector, first row, 1 times -1 plus 2 times -1 plus 3 times 1 equals -1 minus 2 plus 3, which equals 0. Second row, 2 times -1 plus 4 times -1 plus 6 times 1 equals -2 minus 4 plus 6, which equals 0. Third row, 2 times -1 plus 6 times -1 plus 8 times 1 equals -2 minus 6 plus 8, which equals 0. Fourth row, 2 times -1 plus 8 times -1 plus 10 times 1 equals -2 minus 8 plus 10, which equals 0. Every row gives 0, confirming the recipe works for any shape of matrix. Let's now see the full algorithm laid out from start to finish. Step 1, eliminate A down to echelon form U. Step 2, count the pivots. That gives you the rank R. Step 3, classify the variables, R pivot variables and N minus R free variables. Step 4 offers two paths. The standard path, back substitute on U to find the special solutions. The express path, continue elimination all the way to reduced row echelon form, read off a -f, and write down the null space matrix N immediately as -f on top of the identity. Either path leads you to step 5. The null space equals the span of the special solutions. The express path through RREF makes step 4 completely mechanical. No back substitution needed. And importantly, this algorithm works for any m by n matrix of any rank. Let's zoom out and see the big picture. Reduced row echelon form is the canonical form of any matrix under row operations. Every matrix has exactly one ref. It is unique. That means the null space structure is encoded in a completely standardized way, regardless of the matrix size or rank. Here is the generic RREF matrix R with its block structure. The identity block I in the top left and the block F in the top right with zeros filling out the bottom. The identity block I tells you which columns are pivot columns and it reveals the rank of the matrix. In the block F tells you exactly how the free variables relate to the pivot variables. And from F we get the null space matrix N equals -f on top and the identity on the bottom. This formula hands you the special solutions without a single step of back substitution. Let's summarize the 3 key facts. Fact 1, every matrix has a unique ref. Fact 2, the pivot columns identified by I reveal the rank. Fact 3, the free columns identified by F reveal the null space through the formula N equals -f over I. We have now fully solved AX equals 0. So what comes next? The natural follow-up question is, what happens when the right-hand side isn't 0? And that leads us to the complete solution of AX equals B.